Welcome to topic 9.1. For this unit, we're going back to the world of math and we're going to start connecting things together we've been working on this semester. So you definitely need your calculator. I would highly recommend that you are not using your cell phone as your calculator, but getting your actual scientific calculator out. The other things that you need for today are your periodic table, and then I'm going to call this the mole map, this reference table. If you don't have the ability to print, it's a very easy resource to set up on a piece of paper to help kind of keep track of. So the next topic we're getting into is what's called mole conversions. And basically the mole is like the big door that we've been trying to get to all year long, because it's how chemists quantify atoms, molecules, and what's called formula units, and even ions. So we have a way of quantifying them. And so there's different things we've been using. And like I said, it's a snowball effect that lots of things are going to start connecting together in this unit. And so the big thing is, if you are not getting the correct answers, but you're setting up the work the way that I am in my videos, it's just a calculator issue on how you're typing it in. The most useful way for me to help you is you need to take a picture of your calculator with how it's typed in, so I can try to help you with it and follow along with how I recommend that you do type it in. So like I said, we're going to kind of jump right in. And so the first thing is, you're probably thinking, what in the world is a mole? So we're not talking about the mole on your skin, and we're not talking about the fuzzy little animal. Like I said, chemists have to have a way to quantify when we're looking at atoms. And that's mainly what we're going to talk about today, is atoms, and not so much molecules and that, or compounds. And so the mole, and like I said, chemists, we're lazy. If there's a way to abbreviate it, we're going to. And so the mole, we whop off the E, and just like grams is G, we use MOL for mole. And so it's a way of counting. And so the official textbook definition of what is a mole is it's the amount of a substance being an element or a compound, that contains as many particles as there are atoms in 12 grams of carbon-12. And so it's basically no different than any other kind of unit of measurement. It's like counting by dozens. So like we know that if you go buy 12 donuts, you are buying a dozen of donuts, or that if you have 12 inches, you have a foot. So we worked on conversions at the beginning of the year, and we used them in some of our units, mainly in first semester. Well, guess what? Conversions are coming back today, and we're going to do that using the mole. So it has a constant that we can use for quantifying how many atoms or molecules or ions or formula units we have. It came along from a chemist named Avogadro, and his constant, 1 mole of a substance, like 1 dozen, is that there is 6.022 times 10 to the 23rd atoms, molecules, ions, or a formula unit in a mole. And so I believe this is a sextillion. And so if you think about that, that is a very, 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 very large quantity. And so I'll also have you guys watch a video to help explain what is a mole. And so this first part of the notes is kind of set up to help you with how in the world do we go about converting. So before I discuss that, this is the mole map. And we're not using all of this today, so I'm going to refer back to it off and on. We're going to mainly kind of use these bottom pieces here today. So this is like a map, no different than a map that will show you how to get from one town to another. This shows us how to convert from one unit to another unit. So we're going to start showing you how to count representative particles. And there's some different units that we use for that. So things like an element, we count with atoms. So like aluminum is made out of aluminum atoms. Carbon dioxide is made out of a molecule. Molecules are covalently bonded together. And again, we're lazy. So you could abbreviate a molecule as MCule or M''CULE. The other thing we can use to count representative particles is what's called a formula unit, with this really snazzy unit of an uppercase F period, uppercase U period. So it's not what you might think it stands for. It stands for a formula unit. So if you want to know how many atoms you have in a mole of a substance, this is the sense of direction that you're going to use. You're going to use Avogadro's constant to convert. And if you have atoms and you want to know how many moles you have, you use Avogadro's constant. So this gives you the sense of direction of how to set up that conversion factor. And that's the first leg of our map that we're going to utilize today is how to go from a representative particle, and we're going to start with working with just atoms today, going to a mole. So in this first example, we're converting atoms to moles, and this kind of gives you, again, like the roadmap, a way of setting it up. So in example 1, it asks how many moles are in of magnesium are in 1.25 times 10 to the 23rd atoms. And so when we go to set this up, when we think back all the way to conversions, where I took and said, you have 54 inches, how many feet do you have? We always describe problems with two parts. You have what's called a given. The given has two pieces. It's a quantity with a unit. The other thing that you have is the unknown, what you're solving for. So we're solving for moles. So the first thing that you're going to do here is we are going to write out our given. And I'm going to have to turn the page a little bit because of me being left-handed, and I'll twist it around and hopefully it's easier for you to read. So we have our given of 1.25 times 10 to the 23rd atoms. I cannot emphasize this enough. These are measurements. Measurements have units. There's no abbreviation for atoms. You will be okay writing it out, I promise you. So from here, we set up a conversion factor. Going back all the way to the beginning of the year, if we had 3 feet and I wanted to know how many inches it is, we would set up our conversion factor. Again, when you divide a unit by itself, it cancels. And we know the relationship between these two is 1 foot is equivalent to 12 inches. AKA you multiply them and you get 36 inches. That's the exact same thing we're doing, but with really small particles like atoms. So we use Avogadro's constant. So again, you have this to help lead you in your sense of direction, or you have this one here. So we're starting at atoms and we want to get to moles. So atoms is a representative particle. We want to get to moles. Our conversion factor relies on using Avogadro's constant. So we're going to say that 1 mole is to 6.022 times 10 to the 23rd atoms. I know that I need atoms to go in the bottom of my conversion factor. So these divide and they cancel. Because they divide canceling, we're left with moles, which is the unit the problem asked me to find. Now, how in the world do you put this into your calculator? If you have any kind of graphing calculator, this is going to follow the same process. We're going to take 1.25. We're not going to do this whole times 10 thing. See this EE key? It's found on the comma button, which is above the 7. You need to hit your second comma. That will select the EE function. This stands for times 10. All that you have left to do is put in your exponent of 23. Divide, and we're dividing by Avogadro's constant, 6.022 times 10 to the 23rd. So to do that portion, you do second EE 23. Now, if you have a TI-30X that's somewhat similar to this, it's pretty much the same thing. You do 1.25, second EE, which is also above the 7. Put in your power of 23, divide by 6.022, second EE 23. Now, these are the two most common models of calculators used. If you have a different model, have no fear. Just take a picture of it, and I will gladly help you out with how to use your calculator with these. Again, if you take a picture and send it, it's much easier for me to help you. Now, another wonderful thing that is chemistry is we answer with sig figs. That's another thing that's been a very, very long time since we've used, because it's been a long time since we've done anything mathematical. When we take a look at this, our given is what decides our number of sig figs. And when you are counting sig figs with scientific notation, remember you count just this piece here, the 1.25. 1.25, if you look back in your notes, we did that wonderful Atlantic Pacific rule. This is Pacific for present. There is 3 significant figures in this number, meaning we keep 3 significant figures in our answer. The 0 in front doesn't count, so we get 0.207. That 5 rounds it up. So our final answer is 0.208. And our unit of measurement is the mole. And that is our final answer for example 1. Example 2. We are going from moles to atoms. So following our roadmap here, we have this as our given unit. It wants to know a representative particle, specifically number of atoms. So what we have is our given, 2 moles. We go ahead and set up a spot for a conversion factor to go. We're going from moles to atoms. So we use Avogadro's constant with, again, 1 mole. My given unit is a mole. That is why 1 mole goes in the bottom to cancel them out when they divide. Avogadro's constant goes in the top. So this one, to solve, we are multiplying versus dividing. So I'm just going to work it out on this one calculator. Again, if you are not getting the same answers as me, it's how you're typing it in. You need to reach out so I can help you. So we're going to take 2 times 6.022 second EE23, and I get an answer because of my 2.0. This has 2 significant figures. My answer can only have 2 significant figures. So I can only keep the 1.2. Now, you have to be very careful, especially with mole conversions, is notice this E24. So read all of your answer through. So that means that this is times 10 to the 24th power. So my answer is 1.2 times 10 to the 24th. Times 10 to the 24th does not count towards sig figs, only the base part of the number, this 1.2. This is a measurement. Moles cancels, I'm left with the unit atoms. And this is the answer to example 2. So the next 2 independent practice problems are kind of working through the same thing. And we're going to introduce just a different particle. So instead of atoms, we're going to talk about molecules. So these are held together with covalent bonds. Therefore, they are a molecule. So just like before, in this first one, it says how many molecules of N2. So we are solving for molecules are present in 3.50 moles. You start by writing your given, set up a place for a conversion factor to go. You can utilize your mole roadmap. We have moles. It wants molecules, which is a type of representative particle. So to get there, moles goes in the bottom, Avogadro's constant goes in the top. Again, we need units to cancel. So 6.022 times 10 to the 23rd. So the only thing that's changed is we are no longer talking about atoms, but it also applies to compounds or things that are molecules. And so we are going to label this as MCules for molecules instead of atoms, and 1 mole is still in the bottom. Like before, moles are going to line up to cancel. So what this is telling me is because both are in the numerator, we are multiplying to solve. And we get this calculator on my way. So we're going to take 3.5 times 6.022 E 23rd. And this has 3 sig figs. So my answer can have 3 sig figs. So I can keep the 2, the 1, and the 0. The 7 that comes after it's going to round it up. So my answer is going to be 2.11 times 10 to the 24th. This is MCules, and I'm done. Last problem. How many moles are present in 1.5 times 10 to the 23rd molecules of chlorine? So we have our given, it's molecules. We're changing it to moles. Write out your given. And set up a spot for a conversion factor. So the only thing that we've worked with so far is this leg of the map. So it's just inverse of each other. It just depends on what direction you're going. Because we are starting with molecules, molecules must go in the denominator to cancel. Molecules pairs up with Avogadro's constant, so 6.022 times 10 to the 23rd. That's equivalent to 1 mole. So this one is a division problem to solve. 1.5 E23 divided by 6.022 E23. 1.5 has 2 significant figures. So this means I can only keep 2 sig figs. My leading 0 to the left of the decimal doesn't count. So the first place that is counting is the 2. And I can keep the tenths place, or excuse me, the hundredths. That 9 is going to round it up, so my final answer is 0.25. Molecules has canceled. My unit is moles. So this is a quarter of a mole. The other thing I want you to look at in this section is what's called molar mass. So typically as chemists, we don't really talk about atoms, molecules, and formula units. We typically talk about moles and grams as the most common measurement and most necessary for many things that lead itself forward into continuing topics of chemistry. So molar mass, like the name implies, is the mass in grams per 1 mole of a substance. So molar mass of an element, so anything off the periodic table, is numerically equal to its atomic mass. It has a unit of grams per mole. So I'm going to show you how we find the molar mass of an element. That's when you need your periodic table. So from here, and let me dig out my periodic table, we are looking for this first example asking what is the molar mass of Ca, or calcium. So when you go to the periodic table to find calcium, atomic number 20, you'll see this number at the bottom. This is considered the average atomic mass. We learned on how those were calculated way back first semester in the atom unit. Typically what I have you guys do is round this off to 2 decimal places. So we will say that the molar mass of calcium is 40.08. So that means we have 40.08 grams per mole. So when you say miles per gallon, so if your car gets 30 miles per gallon, that means you can take a 30-mile trip and only use 1 gallon of gas. So this is saying to have 1 mole of a material, you need 40.08 grams. So each element and compound has its own unique molar mass to get to the point of having Avogadro's constant. So again, we can compare these numerically. So magnesium, you go to its spot on the periodic table. It's atomic number 12, 24.305. You can cut that off to the hundredths place, so we'll say 24.31 grams per mole. And that's how you find the molar mass of an element. We'll talk more about molar mass of compounds in our next topic. So we're going to work on one other branch of our mole map today, and that's how to get from here to here. So how do you work with mass, which we measure in grams, to moles? And so that all relies on knowing the molar mass of the element you're working with. So in example 1, we are going from mass to moles. It asks, how many moles are there in 30 grams of carbon? So like we've been doing all along, we have a given. We have 30.0 grams. And the one thing I would recommend that you start getting in the habit now is labeling it with the what. So in this case, we're talking about carbon, so I'm going to include the symbol for carbon, C. It wants to know how many moles. So again, when you look at your mole map, and we are going from grams to moles, to get to that destination, you need its molar mass. So to get your molar mass of carbon, you go to your periodic table. So when you find carbon on your periodic table to 2 decimal places, its molar mass is 12.01. Unit is grams per mole. So this is the part that tends to get sticky for students on figuring out what goes where. So this line reads as per. This line reads as per. These both mean division. So this is what we separate. We separate the mass from the mole. Our given amount is in grams. So this piece of the conversion is what's going to go in the denominator, 12.01 grams. The piece that's left over, this per mole, really means 1 mole. So how we're solving this is no different than what we did up above. The only thing different is we're talking about it now in mass, which is much easier to work with because in a lab, when you're using moles, you tend to use a scale. And so you could measure things with grams in a scale. Or in a lab with a scale. So 30 divided by 12.01. Looking at my given has 3 sig figs. So I have 2.49. That 7 rounds up the 9, which then rounds up the 4. So what you end up with is 2.5, but that is only 2 sig figs. If you remember, what we can add on to make this have a third sig fig is a 0. Grams have canceled. We're left with moles of carbon. And that's how you solve example 1. Now, in example 2, it asks how many grams of helium are in 2.0 moles. So our given is moles. We want to change it to grams. You start by writing your given. Again, I'm going to include that this is He, or that we're working with helium. Looking at your roadmap, we have we have moles, and we want to know how much in terms of grams are we talking about. So to get there, you need molar mass. So you go to your periodic table. We look for helium. It's atomic number 2. Helium has a molar mass of 4.003. Cutting that off, we're going to just say 4.00 gram per mole. So in this problem, my given is moles. So this piece is going to be the denominator of my conversion. That means the mass, 4 grams, is the top. All we're doing here to solve is multiplying. So 2 times 4 is 8. This 2.0 has 2 sig figs. So to have 8 with 2 sig figs, we're going to say 8.0 grams of helium. The last example then is it asks, what is the mass of 2.54 moles of bismuth? So my given is 2.54 mol of Bi. I need to get a molar mass because it's asking for mass. So I'm going to find bismuth on my periodic table. Bismuth is atomic number 83. It's 208.98. So as your atomic number goes up, your molar masses are going to get much larger. Okay, so we have our molar mass. So that's going to help us decide how to set things up. My given is moles. So because my given is moles, moles is going to go in the denominator. That part will be 1 mole. The numerator is going to be the mass of it, 208.98 grams. Again, when converting, only your given determines your sig fig amounts. So 2.54 has 3. So we take 2.54 times that 208.98. Again, keeping my answer to 3 sig figs. I have 530.8. That 8 rounds it up. So I get a final answer of 531 grams of bismuth. And this is topic 8.1, or excuse me, not 8.1, but 9.1 on how to do one-step mole conversion.